Okay, so how do I go from these models, my description of the world, to the training? Because I want these models to actually accurately, more or less accurately describe what happens out there. The idea, as I said, is to use data to set specific values for those parameters. So let's actually start with some data. So here I have like a pre-computed set of pairs. Like this again is simple linear problem. So now I have like my variable here is independent value is the first one, and the dependent value that I want to predict is the second one. So now again, if I have my model definition, which is this one, write this is unusable. I can take it like this, and let's say just A and B. So this stuff is defined. And if I apply this to something, why is not okay? This is symbolic. I don't want something symbolic. I want something concrete. So I need to start somewhere, and I'm gonna start just putting random values in. So here I put like minus 0.3, 0.1. And if I apply this on all the first element of a pair, I get a prediction out, which is completely unrelated, of course. These values are random. This is completely unrelated to the actual values that I want to predict. Yeah. But this is a starting point, because now I can define, starting with this, like a measure of how good or bad, in this case, I'm performing at this task. And this is typically called like cost function, or loss function is the most common. In other fields, it's called utility function. It has several names, like it's called free energy in physics. It really depends where we're coming from, but it's always like very similar concept. It's in our case, is describing my average error, and it's something that I want to minimize because I want the error to be as small as possible. So let's start with a very common formulation for the error, which is mean squared differences. Yeah. So I take all my, this is all my predictions, depending on the values of parameters, and this is the actual values, and I take the difference square, and I take the mean out of this, and I just define a function. So now my function, this is very important. My function, once I have defined it on the data, it only depends on the three parameters that I have in the model. So given the choice of alpha and beta, this will give me a number, a single scalar real number. Yeah. And now what I can do, for example, I can, if I set alpha to something like 0.1, I can plot several values for beta. For example, here from -2 to 2 in steps of 0.1. And you see that this is what we have here. This is a particularly simple problem, and you can solve it, with the naked eye, and you can see that around here minus 0.4, 0.3, probably minus 0.45. It will be the optimal value for beta. But of course, we want to set up a more general system to do this. Okay, so to find the minimum, we start by taking the derivatives. So this program or function in this case is very simple. I can just take the derivative here, and you see, I noticed it was dark, so I have written this down. So when you have this problem, it's because you have defined something that you shouldn't have, so you can always undefine it, and we are back at being symbolic again. So here you see that this was a function, and again, the derivative is closed form and is a function itself. So this is the derivative of my loss for alpha, and it depends on alpha itself and beta, and this is the derivative for beta. So now I can use something like solve, and solve this system equation equal to 0, and this will give me exact solution. Actually, this is what was 0.04. I have bad eye, apparently. My eye solver wasn't that good. And you see that this is a quadratic function, and is of course quadratic because we decided that it was quadratic here. Yeah, we can, instead of saying power of 2 here, we could say simply, I don't know, something like abs. Yeah, if you do this, we get a different. Yeah, it's complaining a bit because it cannot invert abs. This is why we use squared. So, but in principle, you can solve it not with this function, but there are ways to solve it. You can use power 4 or whatever you want. You typically want something that is positively defined and has it well behaved. So we tend to stick with what it's simple and works. Yeah, and this is the plot of this quadratic function. You see, it's a product of parabola here, a parabola here for one variable and one here for the other variable, and it has a well-defined minimum here. Okay, so how do we find this point? I gave a hint before because I say let's start from a random place and measure the error and figure out how to minimize the error. So one trick that is always done to do this is gradient descent. So how do we do? We wanted something that is able to gently push us towards a solution. So one trick is that you start from the point, and then you look, instead of trying to find the minimum, which requires to digest all the data, and is a global operation. Let's say we are here. Let's say you do something very local. You stay here and you say, okay, if I'm here, in which direction should I go to go towards the minimum? You don't know where the minimum is, but what you know is that, for example, there's a slope, and that the slope is going in this direction. Yeah. So in this case, you say, if I'm here, I think I should just go down here. I should go in this direction. Like this is these lines of the same height. So if I go perpendicular to these lines, this is a good bet that I'm going towards my minimum, or like a minimum. Yeah. I'm gonna say a bit more about global and local minima in training later. So what I do, I define a function here that is basically just I normalize the derivative just because I don't want to do steps of different size depending on how steep it is, or maybe I do want to do that, but right now I don't. So now what happens if I start from my random point from before, and I put in I put my point into my function? This tells me you see that this arrow is not pointing towards the absolute minimum. It's just pointing in one direction. So if I'm here, this my function is telling me just move here. And the thing is, now I have an iterative method that I can easily generalize, and I say, okay, if I'm here, where do I move? And if I'm here, where do I move? Yeah. So I can just you have a nice function nested list. And I can write here this what is called pure function that takes my my point, which is like 3, 1. Takes my derivative at that point, and this here I put a small step because I don't want to to move too much. I just in principle I would want to do an infinitesimal movement, like very very very, very small. But we don't have our infinite time to solve this stupid problem, so we want to move over like a finite amount. And here you see that if we can learn a lot of things by playing dynamically with this step. You see, if my step is big, I immediately go in a good area where my solution is, but then I never really find the solution because I move too much. Yeah. So like the point is, if you are like here and you move a lot, you end up here or here or here. So you need to reduce your movement rate, and many methods are adaptive, and they reduce the step, the how much they move when they are like close to the minimum. Of course, if the step is too small, you never reach. It takes very long time to reach the solution. Yeah. So you like adaptive methods are fun, and you can you can be adaptive. You can cut a lot of corners with neural networks. You can be adaptive in a very silly way. You do like x hundred steps with a big step, and then you cut it, and then you cut it. So you don't need. You're not forced to go with something like super sophisticated, or you can use something like Adams, which is like we have like different optimizers in the system that can do this for you. Okay, so what is typically used in neural networks is not gradient descent, though, is stochastic gradient descent. What is the difference? I should have put some visuals here, but let's say when I compute the error, I don't compute. Let's look at this one again. I don't compute this at one point. I do the mean across my whole data set. So as I said, for neural networks, you don't want to use everything. You want to look at the data a bit at a time because it is not going to fit in your memory. So what you do, imagine that instead of having, I don't know how many points are these, like, well, let's figure it out. I do length of data. It's 20 points, yeah. 20 points will fit, but imagine it's 20 million points. Maybe I just want to measure my loss on 2,000 at a time, yeah? So I randomly select 2,000 points, I compute my loss, and I do a little step. And then I do it again, and then I do it again, yeah? So at some point, I will exhaust my 20 million points, and I can keep cycling through them, getting better and better at predicting it. And this kind of skips the problem of having too much data altogether. You never have too much data for training. It's just a matter of like how many compute nowadays are called, like compute resources you have.